Good morning. I'm going to be talking about domain walls and skyrmions in the material TmIG. So TmIG is also known as tellurium iron garnet. I'll be talking about some of the material properties of it, as well as domain walls and domain wall switching in the material. Then I'll be talking about chiral magnetism, Dialyshinsky-Maria interactions in the material, and skyrmions. So TmIG is a rare earth garnet. You can see an image of the garnet structure on the slide. In this case, the B and C sites are both taken by iron. It's also a magnetic insulator, which means it has a high resistivity to electrical current, but is still magnetic and is often paired in bilayers with a conducting metal. In the case of TmIG, this is typically platinum. It exhibits ultra-low damping and long magnon decay lengths. Magnons are basically a collective excitation that can be modeled as a spin wave. Coupling to heavy metal layers can excite and detect propagating magnons. And this material also exhibits perpendicular magnetic anisotropy. So domain wall switching in TmIG is driven by spin orbit torque, which is something we talked about last class. Domain walls can be switched with as low as a field of 2 orsteds. When current is applied, there is a switching of domain walls, which is facilitated by the spin orbit torque. To achieve switching by spin orbit torque, an in-plane field is applied to the current direction. This breaks the magnetization's rotational symmetry. The threshold current depends on whether there is an initially present or reverse domain. So large current is necessary to nucleate a reverse domain from saturated TmIG. But in unsaturated TmIG, there is high velocity propagation of domain walls. Switching also only occurs in the deposition area of platinum. So the image on the slide, part A shows the switching percentage for the field given. And then B and C show domain nucleation and expansion for B and compression for C. These come by through MOC, which is the magneto-optical Kerr effect, which I believe someone's going to be talking about in a few lectures. So domain walls have something known as a chiral structure. Chirality refers to the handedness of something, of a material. So if it has like a non-superimposable mirror image, it's chiral. So TmIG has well-defined chiral structure. It's left Neal domain walls in TmIG to an intermediate Neal block domain walls in TmIG and PT bilayers. It also exhibits finite DMI. So the images down below show domain wall motion during a pulse, as well as skyrmions. So interfacial DMI stabilizes chiral spin structures such as skyrmions. DMI is an antisymmetric exchange interaction, which basically means an interaction between neighboring spins of electrons. The chiral exchange interactions come from broken spatial inversion symmetry. Interfacial DMI is found at room temperature due to antiferromagnetic spin dynamics. While this is rare in bulk materials, it can be engineered in interfaces. In this case, it originates from the oxide-oxide interface between the substrate, gadolinium gallium garnet, that the TmIG rests upon. DMI scales with inverse thickness to TmIG, which means it's not dependent on the PT bilayer, but is dependent solely on TmIG. There's another effect known as the topological Hall effect, which is where an electron spin basically follows the skyrmion, as you can see in the image on the slide. The topological Hall effect, it depends on in-plane bias and the thickness of TmIG, and it can also be tuned with temperature. TmIG can be used for low power skyrmion-based applications, spin orbitronics, and magnonics, particularly magnetic waveguides and tailored magnetic bands. There's also something called magnetic bubble memory, which was popular a few decades ago. It's basically the concept was movable magnetic bubbles, which are the bubbles are small magnetized domains. Previously, the size was too large and the bubbles required an on-chip magnetic field generation, which made it pretty much like unfeasible. However, skyrmions could bypass these, and their existence in TmIG makes it a good candidate for magnetic bubble memory. And that's all I have for today. Any questions?
Yeah, could you just explain, like I'm a really little kid, what is a skyrmion? Because I've completely missed that still.
Oh yeah, so a skyrmion is kind of like a spin texture. So if you imagine like a vortex, for example, that would be an example of a skyrmion, or like a point, like multiple spins that like come up towards this point, that would be an example of a skyrmion as well.
I think that the skyrmion can be differentiated from the vortex because it's has chirality that's induced by some kind of exchange interaction, the Distance-Moria interaction. So that once it's created, it is stable in that way. Yeah. So a vortex is slightly different from a skyrmion, but they both have a vortex-like structure. Yeah. Is that clear, Elena? You can see the little cartoon of what it looks like, right? The little hedgehog cartoon.
Yeah, that makes it's a little better.
Any more questions?
I have one.
Yes, go ahead.
So usually for ferromagnetic materials, you'd have some sort of readout like with an MTJ or something. For this type of material, what kind of readouts can you do besides MOC images like you've shown?
I believe there is also nitrogen vapor magnetometry that has been used to see images, but those are the two that are primarily used as far as I know.
So for electronics, you would analyze a MOC image or something?
I'm honestly not very sure. There aren't too many like electronic material devices created with TmIG yet.
I think Sam is putting out a challenge, which we are also facing because we have some TmIG, but it's how to actually like electrically measure these skyrmions because they are so scaled in it, right? And these centers are nitrogen vacancy centers.